Hello, Matt here from chemistrystudent.com. In this video, we're going to look at sp3 and sp2 hybridization of carbon. We're going to talk about what sp3 and sp2 hybridization actually is, link the hybridization of atomic orbitals in carbon to carbon's ability to form 4 covalent bonds, and show the hybridization that is occurring when 2 carbon atoms form a pi bond. Sigma and pi bonding and electron configurations have been covered in separate videos. Check the links in the description below. Before we talk in detail about hybridization, there are a few essential ideas you need to be comfortable with. Within an atom, negatively charged electrons exist in regions of space called orbitals that surround a positively charged nucleus, made up of protons and neutrons. Each orbital can hold 1 pair of electrons. There are different shaped orbitals that electrons can be in, depending on their distance from the nucleus in an atom. The orbital shape just refers to the area that an electron pair is likely to be in at any one time. They are essentially constantly moving around within this space. Sigma bonds are covalent bonds that form from the direct overlap of atomic orbitals from 2 atoms. Electrons in the bond are close to the nuclei of both atoms, giving a high level of attraction that is hard to break, making sigma bonds very strong. Pi bonds are covalent bonds that form from the sideways overlap of p-shaped atomic orbitals from 2 atoms. Electrons in the bond are further from the nuclei of both atoms compared to those in a sigma bond, giving weaker attraction that makes the bond easier to break. Recap done? Let's go. Carbon is able to form 4 covalent bonds. You probably know this and can easily see it when we study carbon-containing compounds, such as methane and ethane. The thing is, carbon forming 4 bonds doesn't quite make sense when we look at its electron configuration. An atom of carbon has 6 electrons, meaning the electron configuration for an atom of carbon is 1s2, 2s2, 2p2. This gives 2 half-filled p orbitals and 1 empty p orbital in carbon's outer shell. Based on this electron configuration then, carbon should only be able to form 3 covalent bonds, 2 by using 2 half-filled p orbitals and a third coordinate dative covalent bond by sharing a full electron pair from another atom using the empty p orbital that it has. We know this doesn't happen, however, and as we've said, carbon makes 4 bonds with other atoms. To explain this then, we have to slightly alter our ideas of atomic orbitals and bonding. The result is a model referred to as hybridization. Now, hybridization doesn't only occur for carbon, and it's actually a mathematical idea. But as this video is about carbon hybridization will be the focus, and we will leave out the advanced mathematics. Hybridization describes how as an atom of carbon starts to bond to other atoms, its outer atomic orbitals rearrange and mix themselves to form new, identically shaped orbitals, all with the same energy and, most importantly, each with 1 electron in from the carbon. Each new orbital forms a single sigma bond to another atom. The 4 new orbitals formed are slightly higher in energy than the 2s subshell and slightly lower in energy than the 2p subshell. The orbitals are described as hybrid as they are formed from different types of atomic orbital, and as sp3 because they are formed from 1s orbital and the 3 p orbitals in carbon's outer shell, given sp3. Carbon atoms that have hybridized in this way when bonding with other atoms are referred to as sp3 hybridized. The sp3 orbital shapes are kind of a bit of a mashup of an s orbital and p orbital, and they are described as having s character and p character. Basically, how much the orbital shapes are s orbital like and how much they are p orbital like. As the orbitals are all the same energy, the electrons inside them will cause equal repulsion between all four, meaning the orbitals try and get as far away from each other as possible and end up pointing away from one another, with the maximum possible distance between them. This gives an angle between each of them of 109.5 degrees, a tetrahedral arrangement. The sigma bonds they form, therefore, have a tetrahedral arrangement around the central carbon atom. For example, when a single carbon atom bonds with hydrogen, methane, CH4, can be formed. As hydrogen atoms bond to the carbon, the outer two s and two p orbitals in the carbon atom hybridize and form a set of sp3 hybrid orbitals, each with one electron from the carbon atom in. This results in the formation of 4 sigma bonds between hydrogen atoms, that also have one electron in their 1s orbital, and the carbon atom, with the bond angles all being 109.5 degrees, given a tetrahedral structure. The carbon is said to be sp3 hybridized. So far, we've only dealt with sigma covalent bonds being formed by carbon atoms. However, we know that carbon can also form double or pi bonds with other carbon atoms. And an sp3 hybridization of orbitals wouldn't allow this to happen. This is because when forming a pi bond, p-shaped orbitals from 2 carbon atoms have to overlap sideways, above and below a sigma bond between the 2 atoms. If 2 sp3 hybridized carbon atoms bond together with a sigma bond, the remaining 3 sp3 hybridized orbitals aren't really p-shaped and they are all pointing away from each carbon, meaning there is no way that 2 can overlap sideways and form a pi bond. In order to form a pi bond then, each carbon atom has to have a half-filled p orbital that isn't hybridized. For this to be the case, only 3 of the 4 outer orbitals of the carbon atoms can hybridize, the 2s and 2 of the 2p orbitals, leaving 1 of the half-filled p orbitals unhybridized and free to make a pi bond. This means 3 hybrid orbitals can form, and they are referred to as sp2, as they are formed from 1 s orbital and 2 p orbitals, sp2. Now, as a sigma bond forms between the 2 sp2 hybrid orbitals from 2 different carbon atoms, the unhybridized half-filled p orbitals on each atom can overlap sideways with each other, forming a pi bond. Due to the electrons in the p orbitals repelling the electrons in the sp2 hybrid orbitals, the sp2 hybrid orbitals all end up in the same plane, essentially flat. The sp2 orbitals also repel each other, meaning they end up equally far apart, giving bond angles of approximately 120 degrees and a trigonal planar arrangement. For example, when 2 carbon atoms double bond together and form the molecule ethene, each carbon atom has 3 sp2 hybrid orbitals and a half-filled p orbital. 2 sp2 hybrid orbitals make up a sigma bond between the carbon atoms, and their half-filled p orbitals overlap sideways to form a pi bond. 2 hydrogen atoms are sigma bonded with the other sp2 hybrid orbitals on each carbon, making up the C2H4 molecule. The sp2 hybrid orbitals are all in the same plane on each carbon atom due to repulsion from the p orbitals forming the pi bond. And they all have a trigonal planar arrangement, giving a flat molecule with bond angles of approximately 120 degrees. So, to summarize, carbon is able to make 4 covalent bonds, which is strange, as the electron configuration for carbon, 1s2, 2s2, 2p2, wouldn't predict this as being the case. To explain the fact carbon makes 4 bonds, a model of orbital hybridization is used. When a carbon atom makes 4 sigma bonds to 4 other atoms, the s and p orbitals in its outer shell rearrange and mix, forming 4 identical orbitals that are now called hybrid orbitals. The hybrid orbitals formed are described as sp3, as they are made from one s orbital and 3 p orbitals. The carbon is termed sp3 hybridized, and the bond angle between all 4 sigma bonds is 109.5 degrees. The arrangement of bonded atoms around the central carbon is tetrahedral. When a carbon atom forms a pi bond with another carbon atom, a half-filled p orbital must be present on each atom, meaning only the 2s and 2 of the 2p orbitals from each carbon can hybridize. This forms 3 hybrid orbitals that make sigma bonds, each with a bond angle of about 120 degrees, and the arrangement of bonded atoms around each carbon is trigonal planar. The hybrid orbitals are described as sp2 as they are made from one s orbital and 2 p orbitals. I hope you found this video useful. Please check out other relevant videos in the links given in the description below, and visit chemistrystudent.com for free notes and revision materials.